So, so what the first thing I want to do is to recap what we did last time a bit, and also correct some mistake that I made. So last time, what we show is that we show a linear sketch, right? That have small size, and what we can get from it is that we can get some number such that this number square is really close to norm square of x. Okay. So that's what we get last time. So we can estimate the norm square really accurately with high probability. But if you can estimate the norm square accurately, then you also can estimate the norm, right? Just take the square root to all of this. What you get is like this thing over this, and this is like a square root of 1, which is basically something like, something that looks like this thing. So basically, absolute value of z is like epsilon over 2 delta estimator of the norm. So that's all good. That's all correct. But that is what is not quite correct is here. So before we try to use median of mean trick to get the concentration, right? In the beginning, we just compute z, which is just a projection of x into some random vector g, right? And what we can conclude is that here we show that the expected c square is norm square. So that's what we conclude. But in class last time, I instead said that the expected of norm of c is the norm of x. So that's not true, right? So in general, whenever you have like in general for any random variables here, it's not the same as this thing. This is not the same thing. So that's why I cannot just like take the square root inside the expectation. That's not true. You can come up with some code example. Let's say z is a random variable which is maybe of value 0, 2, and 4, each with probability 1/3. And you can check that this is not true. This is just not true. So this is what we can conclude. And so what I should have said in class is that when you do just one random projection, what you preserve is a norm square, not like the norm square of x is preserved in expectation. Also, the distance square between any 2 points is preserved in expectation. So that's like, so yeah, random projection preserve distance square. Yeah. But yeah, once you boost your estimator to be like epsilon delta estimator, that's when it's not in expectation anymore. That's when you can take square root. Okay, so it's just some subtle point that I make a mistake, but I hope you understand this mistake. So this is thanks to Kevin and Daniel who point this out to me. Yeah, so thanks a lot. Okay. So we have seen like several algorithm, several streaming algorithm, right? We have like streaming algorithm that we have seen is like a frequency query. We have seen what else? Sparse recovery. Also L0 sampling and L2 norm estimation. So this is like several examples, and you can imagine there are more things you can try to ask, but we just gonna stop here. Like this is all I gonna cover in this class, but you see like it's just like really it's really natural setting where you have a stream of sequence of data, and you can only like you have tiny bit of space and you want to know something, and we see that we can do a lot of things. We can store some nice information about like frequency vector x that is of huge dimension, and just compress x into something tiny and still can query something useful about x. Okay. So now what we're going to do today is not really look at this setting of streaming algorithm, but look at the technique that we did, that we have, which is linear sketch. Everything that we have, all of this question that we try to solve, we solve it using a linear sketch. And we will see that this linear sketch actually has really nice application to some other setting too. In particular to distributed graph algorithm. And we call this graph sketching. Okay, so what is this setting? So let me tell you about it. The setting is here. Imagine that you have one server, and then there is like a huge graph. Okay. And here each of the like there is like node in the graph. And maybe you think of this graph as a computer network. That is, each node here is like a local computer. Like just one computer here, and the graph is like, let's say, internet graph, or some huge graph that that just no way to store the whole thing. And so each node here doesn't know the whole graph. It just, what it knows is some local knowledge that is just edges that is incident to it. So node B, what it would know is just all, let's say, like the graphs like this. Then what node V would know is just like U1, U2, U3, U4. So it would just know all edges incident to it. And maybe its neighbor, like, and then also know the name of this guy. Okay. But it wouldn't even know that it wouldn't even know that like there is an edge between the neighbor or not. Okay. So that's all it knows. Like it only know this thing. Okay. So okay. And what each node can do, each node can send some information to the server. Send information to server. Okay. That's what I will allow. And maybe also the server can store some random bits here. So like each node can can communicate with server, let's say. The server can store some random string. Okay. This is just like random string that each node every node can see the same random string from the server. Okay. So I will allow this because so that every node can share some random string, so that when let's say they want to sample some hash function, then they get the same hash function. Okay. So I will allow this. Okay. And now the generic question is like, what we want is that we want every node here to send just one message to the server. If node V send a message MV to server, and the server can read these messages. And then the server need to be able to answer some question about the graph. Okay. So one trivial solution is that every node, right, just send the list of all incident edges to the server. If every node just do that, then the server would know everything about the graph, and then the server can answer anything. But if we do something like that, then the size of this message would be of size n. In the worst case, the message can have, like, you can have n neighbors, like order of n neighbor, and we don't want that. What we want to do is that we want to say that, okay, we can minimize the size of the message and make the size of the message to be like log n or polylog. Okay. So that is the setting. Is it like a question about the setting? Yeah.
Wait, so the server knows nothing about the graph at the beginning?
No.
And it's trying to like figure out its structure?
Yeah. So the server just have no knowledge about the graph. Every node have really local knowledge about the graph. But what we want is that when every node sends some message, some really short message to the server, collectively, this message like is useful for the server to know some global structure of the graph.
So what's the function of the random string?
Oh, this is really just random string. Like there's no function here. Like it's just, let's say it's just a sequence of random coins that you toss. Yeah.
Well, why they imply that they can share the same hash function?
Oh, because if every node here can see the same random string and use like the same sequence of this random string to sample anything, then they would get the same hash function, right? Yeah. Okay. It's like, oh, let's say when I ask, okay, what each node V want to know like 2 random bits, then they would get exactly the same random bits sequence. Okay, so that's the setting. But before we try to answer like any question in this setting, what I want to start with is the one key idea that will underlie everything today. That is how to get some cut information from incident metrics. Okay, so imagine that you have a graph and it had n node and m edges, doesn't matter, that's here. Then we can say that let me define what is in this incident matrix. Okay? The incident matrix is just a matrix where each entry is -1, 0, or 1. And what we're gonna do is like it has n many rows and n choose too many columns. Okay, and this is the definition of B, but maybe it's just better to look at the example. Let's say that this is a graph with 4 nodes. Then I will have 4 rows. And for each column, this is just like a 4 choose 2 columns. And for each column here, I will just look at this column and see if this 1, 2 is an edge or not. If there is an edge, so there is an edge, then I put 1 on one endpoint and minus 1 on other endpoint. It doesn't matter like which one it doesn't matter which endpoint I put 1 or minus 1. Just choose it arbitrarily, but one need to be like one endpoint needs to be 1, another need to be minus 1. If 1 and 3 there's no edge, then this is just all 0, and so on. This 1, 4 there is an edge here, so just put 1 and minus 1 here. So that's incident matrix. And now let me define for each node U. Let me define BU to be just the u's row of B. So, for example, this you can think of this as a vector, and this is B3. Okay. This vector would be B1. Okay. And now, if I say that given any set of nodes S, I will define BS to be the sum of BU over all U in the set. So let's see example. So for example, if I look at B of this set 1, 4, then I would look at this row and this row and then sum them up. So here there is 1 and 0, I put 1. This is all 0, I put 0. And so here there is 1 minus 1, so they cancel. So this is like this is an edge that is like completely inside this. So this is my set, right? So this edge, this edge is completely inside the set. So there will be cancellation. And then for this one, there's 2 and 3. This edge is completely outside the set, and so nothing is there. Like this is just sum to 0. How about this one? 2, 4. What you would get is like you will get there's no cancellation, so you get minus 1 here, and so on. Okay. And if you look at another set, let's say now is like this set, right? So you are looking at this and this sum. And now you see that actually there's going to be a bunch of cancellation. Like for H1, 2, this is going to be cancellation and you get 0. 1, 3 is not, there's no edge. 1, 4, there's cancellation again. And for 2, 3, 2 and 3, there's no cancellation because there's just 1 here. And for 2, 4, that will be cancellation again. You get 0. Okay, so I hope you get an idea. Like, so first, like if I ask, what is BV? V is a whole, like whole vertex set. What is BV?
Just the sum of all the rows.
Yeah, so what is gonna be?
Is that all zero?
This always zero. Always zero. Like 0 is always 0 vector. Because like when you sum every row, like you get cancellation always. Always. Right? And so now like if you actually look at this, can you tell me like when do you get 0 and when do you get non-zero in the vector here? So yeah.
So the non-zero entries should be edges with exactly one endpoint in the set.
Exactly, good. So I repeat, the non-zero entry can be -1 or 1, really just correspond to an edge that cross a set. So one endpoint in a set. Right? If it's completely inside, then you get cancellation. If it's completely outside, you wouldn't even sum it. If it's not an edge, then there's nothing to sum. So non-zero entry correspond to a cut edge. So that's what we exactly get, right? -1 or 1 entries of BS really correspond to the set of edges crossing the set. Okay. So it means, for example, that if I want to know the cut size, right? What I can do is just compute, for example, a 2 norm square of BS. Right? And what it's gonna give is just sum over all edges crossing the cut. 1 minus 1 square, which is always 1. And that's just exactly the cut size. Okay. Good. Question about this? Okay. So now let's see why this observation should be useful. So suppose that what server need to compute is 1 plus epsilon approximation of the cut size. And we want to compute it correctly with high probability. Okay. So then what we can do is just here. Well, each node, right, just compute this norm estimation sketch of BV. So BV is a huge vector, like of size of dimension n choose 2. But when you sketch this thing, you again like compress it to just a vector of size something like constant. And then what each node V need to do is just to send the sketch, not the BV itself. Just send the sketch to server. Now, if the server need to compute the cut size of any node, what it can do is just a cut size of any set S, right? Suppose that the server want to know the cut size of S. What it can try to compute is just sum. Like look at the sketch from all nodes in S, sum the sketch from this set. But you see, the sketch is linear. So the sum of sketch is a sketch of the sum. So that's important. That's why like we like linear sketch. But now this is a sketch of BS. But we know that like from this sketch, we can compute the accurate estimator of the norm square of Vs. But that is just the cut size. Right. So now you see like the message size that each node sends is now just constant instead of n. Make sense? Okay. So if you think about it, like this is quite interesting because like the total size of graph, right? It can be of size n square. Like the graph itself can be dense. The graph can have size n square. But the total size of the message that the server gets from these nodes is just n times this number. So it's like much less than n, like constant times n. So even if the server get information which is sublinear in the size of the graph, the server can still compute some useful information about the graph itself. For example, if they want to just to know cut size of any cut, they can compute it accurately with high probability. Okay, question? Good. All right, then. Should I move on? Okay, so let's see more application. Like, suppose now we instead of computing just one cut size, let's say we want to compute a spanning tree. So the server needs to compute a spanning tree of a graph G. Okay, and we want to do it with high probability. Again, a trivial solution is just to send, like each node just send all incident edges to the server, and that the message size is of size n. Okay, so if you don't know linear sketch before, you might think, okay, if we need to solve this problem, actually there shouldn't be any non-trivial solution. This should be impossible. So let me try to convince you another way around that, okay, we cannot hope to get anything better than n. Okay, so what is that argument? Well, suppose that like so if we call an edge a bridge of a graph if G minus E is disconnected. So for example, if the graph looks like this, then these two edges are the bridges, right? Because if you delete it, then the graph is disconnected. Now you know that if an edge is a bridge, then the server should better know about E, right? Because otherwise, like you cannot use E to connect. Okay. But if you think from the local perspective of any node V, let's say this is a node V. Okay. So a node V, what does it know? It knows this edge. It knows this thing, know this, and know this. And it knows nothing else about the graph. So from the local perspective of V, okay, any node, any edge incident to it actually could be a bridge. right? So any node could be a bridge. So maybe I should send everything. But yeah, so that's like kind of argument why maybe I should, like the size of the message should be like linear in n, because I might need to send everything. But you will see that you can use actually polylog this again. And maybe once we are done with this, maybe you try to answer me how come, like what's going on, like how come we can bypass this barrier of sending a bridge to the server. Okay. So we're gonna just get a message of size polylog n. Okay, so before I tell you the algorithm, let me recall some algorithm for computing spanning tree called Borufka algorithm. Have you seen it before? Borufka? Okay. So then that's good. It's a simple algorithm actually. Where is it? So it's an algorithm where initially you think like each node as is its own cluster. Like so that in the beginning there are n clusters. Okay, every node is its own cluster, and then what we would do is that for each cluster, which initially is just every node, each cluster will choose one edge going out of it. So this node maybe choose this edge. This node might choose this one. This node, okay, it might choose kind of the same. Like it doesn't know anything about another cluster, so it just choose some edge going out of a cluster. Okay. So once all the clusters have chosen one edge out of a cluster, then what you're gonna do is you add the chosen edge into your tree. You plan to construct a spanning tree, so you add this edge into your tree. As long as it doesn't create a cycle. So for example, this edge can be added. This one you add it, okay, and this one you add it here. This one you maybe add this, and if you add this guy, then this one you shouldn't add into your tree because it would create a cycle and you don't get a tree. So just this. And then once you add all these edges without creating cycle, this chosen edge would merge the cluster. Okay. So yeah, this thing would become one cluster. And that's when you're done with the first round. So may I ask you like how like what's the maximum number of clusters after one round? Yeah.
-1.
N-1. Well, that's too big actually. So you maybe someone can try again, or you can try again.
Is that n/2?
Why is that?
Because I think you got to merge at least two independent clusters. So the size decrease.
Yeah. So basically, in the worst case, like you know that every cluster will be merged with another one, and in the worst case, like what you get is like something like what you get is something like a matching. A cluster look like a matching, perfect matching, and that would reduce the number of clusters to to n half. But you might be even better, like the size of your cluster might be even bigger than 2, and that would even like reduce the number of clusters to less than n over 2. But anyway, the number of clusters is half. And then once you're done with the first round, just continue. Each cluster choose one edge going out of it. And then try to add this chosen edge as long as it doesn't create a cycle. So this one you add. This one you wouldn't add anymore because otherwise it creates a cycle. This one you add. This one wouldn't add. You shouldn't add. And so on. Okay. So you add these edges, merge the clusters, and then continue. Just finish the second round, continue to the next round. Yeah, and so on. And you would be done when there is only one cluster left. Okay. So that's the algorithm. Okay. Question about this? So now, how many rounds can there be in this Borufka algorithm? Yeah.
At most log n.
Yeah. Why is that?
Because like worst case you get n over 2 clusters, so just divide by 2 every time.
Exactly. Thanks. Yeah. So good. So like basically after round I, what you get is like at most n over 2 to the I cluster. So after log n round, you would be done. Okay. So that's the algorithm. But now, given this algorithm, let's see how do we solve our graph sketching problem for spanning tree. So what I'm going to do is just this. Each of node V will use some linear sketch again, but instead of norm estimation sketch, we're going to use L0 sampling sketch. Okay. And we will make like independent copy of this sketch. Let's say we make like log n many copies of this sketch independently. So, and then just send the sketch to the server. All these copies of the sketch to the server. And now, maybe I let you think about it for 3 minutes. What do you think, like how can like with Borufka algorithm, how can with Borufka spanning tree algorithm, how can the server construct a spanning tree of the graph using only these sketches? Yeah. So try to think about it a bit. So one hint to note is that, like, suppose that you have a set S, right? And then if you compute the sketch of BS, then what would it, like the sketch, if you have a set S here in the graph, if you compute this, if you have a sketch of BS, what would it give you? Yeah, that's the first question to answer. Can anyone tell me? When you query this sketch, which is L0 sampling sketch, what does it give you? Yeah.
So just some random edge outgoing from V or incident to V.
Exactly. So, like, you know that the non-zero entry of BS really correspond to edges going out of a set, right? You know, we've seen this before. Non-zero entry of BS really correspond to edges going out of a set. So what LCO sampling sketch will give you is just some non-zero entry of this vector. So it means that it will basically identify one cut edges that go out of S for you. Okay, so now maybe I let you think a bit how to use these sketches to construct the spanning tree. So what we want to do is we want the server to simulate this Borufka algorithm. And maybe you can tell me if the server want to simulate the first round of Borufka algorithm, what should it do? In the first round of Borufka, right? What we want is just we want that each node should choose one. We want one edge going out of each node. What should we do using the sketch?
Sample an edge from every vertex, from each of the sketches, and then maybe choose the smallest or the.
So, yeah, exactly. So, if this node is V, the server has the sketch of BV, right? What does this sketch do? All it can do is just give some edge go out of the set, which is the set here is just one node. So it will just give you one edge going out. And just do this for every node, V. For each node, just query the sketch now for this node U, just query the sketch of BU. It will just again give you one edge going out of U. Okay. So just query the sketch of node V for every node. And that you get one edge going out of each node. Okay. And then given these edges, the server can use this information to complete the first round easily. Okay, now you get you are at the beginning of second round. What should we do now? If we want to get one edge going out of each cluster,
the sketches for nodes in the same cluster.
Mm-hmm.
And that gives you an edge going out of that cluster.
Very good. So if this is node U1, U2, U3, what we have is the sketch of BU1, BU2, and BU3. So we have all these things. But if we add them together, then this is now like, let's call this a set S. Then this would be a sketch of BS. Because this sketch is linear, right? This is like a sum from 1 to 3 of BUI. It's linear. We use this thing. And this is BS. But now from this sketch, if you query it, what will it give you? Well, just one edge going out of the set. Exactly what we want. It gives you this guy. And just do the same thing for each of the cluster. Make sense? Okay. So you see now that for the second round, you can use a sketch again to get one edge going out of it. And you have a third round, and I just do the same trick. And keep doing this until you finish. Yeah.
Doesn't this take like a really, really long time?
Well, it would take linear time, basically. Why is that? Well, so like near linear. So in the sense that here, like you have a six. Let's say here, right? You have a sketch. You just sum up a sketch of constant size, or like polylog size. So that takes like polylog time to sum this thing. Like polylog times the number of the set, number of nodes in the set, right? So if you want, what I mean is like, if you want one edge going out of this, and this is like a set T, you spend something like polylog of T time, polylog times T time to get one edge going out. But the total size of the cluster is n. So summing over all clusters, that's the n. So in each round, you spend like n polylog n times. There are log n many rounds, so that's like, in total, it's just n polylog n total time. That's a good question. Yeah. But now you see that we can really just implement, the server can just implement Borufka algorithm using only information from this sketch. So that's what we're going to do exactly for each round. And for each cluster in this round, we can get one edge going out of a cut just by summing over all the sketch in the set, in the cut. Yeah. And then you complete the simulation. So the total time here is just something like near linear in n. Doesn't even depend on m. Doesn't depend on the number of edges even. Right? Only on edges. Only on nodes. Yeah. This is time. Even if the graph is dense. And the total size of the message that each node sent to the server is something like log cube, because there are log n copies of this, and each sketch is of size log square. Now there is this one detail that I cannot skip. you see here I said that in each round I will actually just use the i's copy of the sketch from each node. So that's like, and there are log n mini round at most. So I just use log n mini copies. So you might ask now, like, why do we need this, right? Why do we need the different copies of sketch for each round I? What goes wrong if we just use the same copies? Okay.
Should not give you the same edge, maybe.
Well, the set that we asked are different for each round, right?
Oh yeah, never mind.
Yeah. So like, what actually is wrong? Okay. So before I answer this question, let me let's look at like a more generic question. Okay. What is wrong when the input of the sketch can depend on the random choice of linear sketch? So this random choice is like the random hash function, like how you sample hash function and so on. And actually, all of the in all of the previous lecture that I taught you so far, you assume that how you this random choice is independent from the input, right? So like when you sample a hash function, that is not depending on the input. It's just completely independent thing. So let's see now what's go wrong exactly when actually there are dependency. If you allow dependency, then something really wrong is gonna happen. So the way you think about the sketch here, you can think of it as a matrix M, right? Because it's a linear sketch, you can represent it as a matrix. This matrix M is like something that you generate using hash function. Like hash function would represent this matrix M. But now let's say that I can choose an input depending on M, depending on your random choice. Then one thing that I can choose is like I just choose input X that's in the kernel of M. That is this just means that Mx is 0. Okay. So now like you see this, I can do this because I allow X to depend on the sketch. On the sketch function on M. Okay. It depends on the random choice of the sketch. But if this is the case, then you see that the sketch of X is just Mx, which is 0, although X is non-zero. Which means that like you have an input which is a non-zero vector, and after you sketch, you look at your array, and all you see is empty array, just all 0. So in particular, although this guy have non-zero norm, what you get is like zero vector, norm 0. Although this guy has non-zero entry, this guy have non-zero entry, like no non-zero entry. So your L0 sampling sketch or 2-norm estimation would fail completely if you allow the input to depend on your random choice. Okay. Okay, now do you agree with this? Yeah. So it's quite important that everything that we have learned so far about streaming algorithm, it's important that the random choice that you use to create the hash function or like to generate your sketch, this random choice is independent from the input. Otherwise, like if the input can depend on your random choice, then like at least we assume this in our analysis, and you have seen that things can go really wrong. Okay. Okay, now let's come back to our question about this thing. Why do we need like a different sketch for each round? So why can't we just do that? Like just for each we just use the same sketch, and just for each round just use the same. Like don't make copies. Yeah. Any idea why we need this? Yeah.
So if BV happens to be like in the kernel of the sketch, then you never choose an edge incident to V, so like it never goes into the spanning tree.
Yeah. Well, yeah. So. But okay, if like the fact that you might be able to choose some input in the kernel, you can do that only when like the input can depend on your random choice. Otherwise, like that would happen with very low probability. Okay, so as long as you assume independence between input and random choice, that will happen. Like this event will not happen with high probability. But yeah, if you can allow dependency, then this can happen with high. Like, you cannot guarantee that it happen with low probability anymore. My point is, you can see that the output like of whatever we do in round I actually is like affect the input in round I plus 1, right? Because an edge that you use to like that the sketch in round I answer, that define the set in the next round that you're gonna query. Make sense? Like you have cluster in round I. This is round I. This guy give you some, like you use sketch of round I to answer some edge. And so now, what you're gonna query next in the next round, I plus 1, is this set. And that set depends on whatever you output in round I. So the input from round I plus 1 depends on output of round I. Okay. But if we want to use the sketch in round I plus 1, we assume that the random choice of this sketch for round I plus 1 should be independent from the input X, from your input. But if you just reuse the same sketch, if you don't have I and I plus 1 anymore, now you see that there are now dependency between input and the random choice. Okay. And so the analysis wouldn't work anymore. So this is a subtle point, so it's actually like what I claim for now is that our analysis, everything in class, assume that the random choice is independent from the input. That's how we prove high probability bound and so on. Without that, that claim wouldn't hold. And if we use the same sketch, they are not independent from each other, and at least our analysis wouldn't work. Okay. The algorithm might work still. Like it's not like if you reuse the same sketch. Actually, I couldn't come up with a way to come up so that you can generate some the cluster in round I is answered in such a way that the input in round I plus 1 is the kernel of the sketch. That seems unlikely still, but there are some dependency. So we cannot use this analysis that we had before. So this is a subtle point, but yeah, just something to be careful. And I think it's actually interesting whether to show formally that actually even if you use the even if you keep using the same sketch at each round, things are still fine. But how to do that formally, not clear to me at all.
So in the actual algorithm, like every round, would each node recompute a new sketch and send it?
Oh, well, you can compute the sketch from the beginning, like make log n copies and send it in one go. Okay, so that's it for this problem. More question about this? Okay, yeah.
So how do you compute all the encoding at the beginning? Because you update the sketch over time, right? But if it's at the beginning, the sketch is an original sketch.
There is no update of the sketch at all, right? Like each node really just send all these things to the server. But what server do is just when it want to answer some, like when given one set S, if it want to get one edge going out of this set, just sum all the sketch in this of all node in the set.
Yeah, that makes sense.
When you do the sum, you do it with the sketches for the next round, right? Like not the sketches that you merged in the current round.
No, I mean like in round I, you just use like just sum the sketch from all node V in S, but use a I's copy.
Right. So
Okay.
the next for round I+1, you would forget about the sketches on the ith.
Yeah, exactly. Just forget about everything else. Use the new copies of the sketch. Yeah. Okay. Good. Yeah, so I remember when I was an undergrad, I was super confused about this stuff, but I hope that you are better than me. Okay. Okay, next thing is a cute stuff. It's called communication complexity, and let me talk about it. So this is like some fun thing that is, imagine that there is Alice and Bob, and Alice have a bit string X of size n, and Bob has Y of size n. Okay, and what's the most important is that Alice doesn't know Y, Bob doesn't know X. X and Y are private. Okay, but now they want to communicate into each other. Let's say Alice only want to send one message to Bob. What we want to optimize is we want Alice not to send too much information. It's costly to communicate. So we ask Alice to send just one message to Bob, but now Bob, using only this message, can know whether X and Y are the same. So one trivial way, Alice can send the whole string X to Bob. That takes n bits. Okay. Can we reduce the size of this message? That's the question. And actually, if you ask for deterministic algorithm for Alice or deterministic protocol, how Alice should communicate to Bob, it turns out that you cannot do anything better than n, really. So why is that? So if the protocol is deterministic, right? The message of Alice, you can think of it as some deterministic function based on X, because Alice has only X. So whatever Alice sends need to depend on X. So that's just some function of X. Okay. And now if the message that Alice sends, f of X, takes only k bits, when k is less than n. Then what you have? So the image of this function is now of size less than the domain. So there must exist two strings, x1 and x2, such that it maps to the same message. But then it means what? It means that if Bob is given like f of x1, then Bob wouldn't know whether Alice have x1 or x2, and he wouldn't be able to conclude whether like y is x or not. Okay, so nothing, you can do nothing non-trivial at all with deterministic algorithm. So now I want you to guess like how much, like what can we do with randomized protocol? Like how many bits do you think we need? Any guess? Just for fun. Log n, okay. Any other guess?
Second log n.
Second log n. Okay.
1 bit.
Anything better than log n? 1?
Sure.
Or nothing?
Maybe constant.
Constant? Okay. Yeah. So, but not 0, right? No one thing is 0 is good. Yeah, of course, right? But yeah. Yeah. Turns out that 1 bit is enough.
1 bit.
Yeah. So that's not a joke. That 1 bit is good. Yeah. So okay. So what we're gonna look at is this. At least with just 1 bit, you can do something non-trivial, and you can boost it with high probability using log n. Okay. So let's see how to do it with just 1 bit. Okay. So what I'm going to allow Alice and Bob to exploit randomness is this. Let's say that, so you have Alice and you have Bob, and then let's say that there is some like a random string that like is on the blackboard, like a very long random string R 1110101111. This is written that Alice and Bob can see. Okay? They can see this random string. They are like on the blackboard. But in the first glance, like this random string shouldn't be useful, right? It's just some random string. It tell you nothing about x and y. But yeah, we're gonna see how to use this random string. So I claim that there is a protocol such that with share random bits with this public information R here, such that Alice can send just a message of size 1 to Bob. And if x and y are the same, then Bob would say, yes, they are the same, always, no error. But if x and y are not the same, then Bob would detect that they are not the same with probability at least half. Okay. And suppose I tell you how to do this. Do you see like how to boost this probability? Let's say I want like the failure probability to be like 1/4. What should I do?
Do it twice.
Yeah, do it twice. Yeah, and so we can repeat we can repeat this and make it just boost the probability to be like a 1/n to the 10 just by repeating log n time. So let's see how to do this with just 1 bit. So what I'm gonna do is just Alice gonna compute this thing. So let's say that like this random string is like R1, R2, R3, and so on. I'm just gonna take like a first n random bits of this random string and compute the sum of Ri times Xi. So like inner product between X and R, mod 2. So just 1 bit, and send it to Bob. and then Bob will compute the same thing, like sum of ri's yi mod 2. And then just say that, okay, if x and just return x and y are the same if this inner product is the same. Okay, now you see that if x and y are the same, then no matter what, Bob will always answer yes. These two things must be the same. But what if x and y are not the same? So let's say that x and y differ at the ith bit. They must differ at some bit. So let's say that that position is I. Okay. So let's bound the failure probability. Bob will fail if it turns out that even though x and y are not the same, then the inner product of x to r and y to r, that's still the same. Bob would fail. But that would happen if this is true, right? So just write down just write down, sorry. This is just x minus y inner product with r, and expand the sum to be overall I, x I minus I, yi, ri, and then maybe I sum overall j here. Okay. And now this is 0. Okay, sorry. This is 0 and this is 0. So these things are equivalent. And if this thing happen, then what I can do is I just move the term of I to one side and the rest is here. But xi and yi are not the same, so this is 1 mod 2. When x and yi are not the same, you get 1 mod 2. But now this is just some number, and now it's like you ask, what is the probability that some random bit is this number? So that's 1/2. Okay, so that's it. So we can get this, and we can boost the probability to anything you like to 1/2 to the k just by repeating for k times. So that's cool. But I want to tell you one more bit, which is cool as well. So you see, here, the catch of the previous algorithm is that I allow this share random string. What if I don't even allow that? I don't want to allow a long random share string R that both Alice and Bob can see. What I will allow is okay, Alice can still generate her own random bits. But if she wants to exploit that, maybe she need to send that random bit to Bob herself, right? Because you see, in this algorithm, Alice actually used n many random bits. So if she want to use n many random bits and send to Bob, that's already of size n. That's big. So what if I don't even allow Alice and Bob to see the same random bits, and what can Alice do? So I claim that we can do the same thing, but now the size of the message is not locked in. So Alice can generate her own private random coin, and she will actually send that thing to Bob. There's no share public random bits here. Okay, so there is a protocol that with private random bits that Alice can send to Bob of size log n. If the message are the same, Bob never makes error. If they're not the same, then Bob can detect that they're not the same with probability at least half. So one background that I'm gonna need here is simple stuff about prime number. So let's say that pk is a k smallest prime number. So you might I'm not sure you have seen this. How big is pk? Is it at most 2 to like how big it is. Can it be 2 to the k? Actually, no. It's actually close to linear. Like the size of pk is something like k log k. Okay. So so that's just good to know. It just means that if you want to represent pk, it takes pk bits, which is log of k bits to represent. Okay, that's one thing I will need. So now, what I want you to think about is just think about x and y as a number of size 2 to the n, because x is it's a bit string of size n, but this is just like equivalent to a number of size 2 to the n, right? Just think of x and y as a number now. Like it's a huge number, but just one number. So the protocol is here. Alice will choose a prime from like 2n many, among, list out the prime from the smallest guy to the 2n smallest guy. Pick that prime randomly. Okay. And then just send this prime number and send x mod p to Bob. So p is at most p to n. So p to n is at most something like n log n, which means that p takes like log n bits, and x mod p also takes at most log n bits. So that's the size of the message. And Bob, what it will do is just given p, now it knows what is p. That's like the only random choice that like a Bob is given from Alice. So just use p. Compute y mod p. And now just say that x and y are the same if x mod p is the same as y mod p. That is p divides x minus y. Okay? That's the protocol. So you see that, and so like it takes log n bits, that's for sure. And if x and y are the same, then Bob will always say yes. All we need to show is like if x and y are not the same, then Bob should say like that detect that they are not the same with probability at least half. Okay. So why is that? Well, let's assume for a moment that x is let's say x is at least y. Okay. So x minus y, you think of it as a number too, which is at most 2 to the n. But now, when x is not the same as y, let me ask you how many primes number p can divide x minus y? So I claim that is at most n. So why is that? Sorry, I need to rush a bit. Because suppose that there are different many primes that can divide x and y. It means that x minus y, the k many prime that can divide x minus y, then it means that x minus y can be factored into this form. It's a prime factorization where each of these qi is a prime number, and there are like some exponent of size at least 1. Right? So each of the prime is at least 2, and it's a product of k many things. So this whole thing is at least 2 to the k. But you know that x minus y is at most 2 to the n. So there are at most k many primes that can divide x minus y. But there are n many guys that you can divide you, but you choose your prime from the set of size 2n. So the probability that your prime that you choose would divide is x minus y is at most 2n, 1 over 2. If you change your set size to be 10n, this would be 1 over 10. Okay? So that's why Bob will detect that they are not the same with probability half. And the same analysis would hold if x is at most y. Okay, so that's it. Like in the homework, you will see how to use sketching to apply to this Alice and Bob setting here. Okay, good. So yeah, good luck with your exam and have a good break. Yeah.